video is all about finding the volume of solids between two functions. So let's get to it. Today we're doing volumes of solid. I'm going to use the same two functions and we're going to do 4 different solids so you can see how it changes depending on the solid that you're using. The first one that we're going to do is squares. So obviously the very first thing you need to do is take your two functions and you need to graph them so you have an idea of what's going on. Now what we're going to be doing with these two functions is we're going to take a square and we're going to slide it between these two functions from the left bound all the way to the right bound, which is where they intersect, and we're going to find the volume that's created. So let me show you what this looks like in a 3D image so you know exactly what it is we're looking for today. Now that we have our two functions graphed, over here on the left-hand side, you see what they look like. Look at the right-hand side and you will see this graph in a 3D space, and I'm going to drag a square through this space so you can see what that square looks like between the two curves. This is what we're doing, is we're moving a square along the x-axis. But now let's look at what that shape will create in terms of volume. So this yellow picture shows you the volume that we're creating when we are sliding the squares along the x-axis all the way from the left-hand side to the right-hand side. So this is the volume that we are going to be solving for. So like you saw in the 3D image, we're creating that volume. So let's take an aerial look at this. If you look down at the function, you will just see the base of the square, which would just be a straight line. If that's an aerial view, all you see is one side of the square. Okay, so we're looking down at it. So pretend this is a square, and I'm gonna pull this square slice out, and I'm gonna lay it down. So this is like a square that I've taken out of there to lay down. So we've pulled the square out. So let's say this part right here is this slice that we took out. So now we need to find the area of the square. So how do you find area of the square? You can just do s times s, right? So the area is just going to be s squared. Whatever kind of notation, length times width, base times height, whatever it is, it's going to be that same side squared. So how do we find the length of this? Well, if you look back over at our picture, it's going to be the top curve minus the bottom curve. That's how you find the height. So we're going to do top minus bottom. And that is how we're going to find the area of the square. Now for volume, we need a third dimension. Of course, that third dimension is going to be the width of these squares. And these squares are all being lined up on the x-axis. So this is going to be a dx problem. So what we need to do is sum up our top minus bottom. This is the length of a side. Square it and have our dx. And then just put in our bounds. And our bounds are going to be where these functions intersect. If you haven't already, put the functions into your calculator, find out where these functions intersect, and you use the x values for our bounds. So now let's put this in with our bounds. Hopefully you found that they intersect from negative 1.414 to positive 1.414. We're going to do top minus bottom. That whole thing has to be squared. So I'm going to start with a big parenthesis first. Our top function, negative x squared minus x plus 2, minus now our bottom function, x squared minus x minus 2. End both parentheses and make sure this guy gets squared. And it's a dx problem because we stacked it along our x-axis. So you can go ahead and put this function right into your y equals. Make sure you are very careful with your parentheses and with the squared. When you put this in your calculator, you should get 24.136 for your final answer. This gives you the volume created by a square between those two functions. So now we have the same two functions, but now we're going to take out a semicircle. So let's go ahead and look at this 3D and see what it looks like when we slide a semicircle between these two functions and the volume it creates. Okay, so now we're going to do semicircles. We have the same two functions. We've got the 3D graph, and now I'm going to slide a semicircle through this space so you can see that we're building the semicircles along the x-axis. Now let's see what that volume looks like. So this yellow thing is the volume that we are creating when we are sliding a semicircle all along that x-axis. Now that you saw the 3D image, let's again look at what the aerial view looks like. So when you look at the aerial view, you're looking straight down, and that's what you see. So let's take this slice out, let's pull it out, and let's lay it down. When we lay it down, here's the slice that we pulled out of the bottom, and here's what the top looks like. That's our semicircle. How do you find the area of that? Well, the area of a circle is pi r squared, so for a semicircle, it's half pi r squared. And now we need to figure out, what is our radius going to be? When you take that slice out, this whole thing right here is your diameter. So to get your radius, you need half of that. Well, what is this piece right here? Well, this is your top minus your bottom function again. So this is top minus bottom, but this is your diameter. So to get your radius is going to equal 1/2 top minus bottom, multiplied by 1/2 pi, and again using your x bounds because it's being stacked along the x-axis. So let's set up our integral. Again, we're using the same bounds because we're using the same function. And you have 1/2 pi. Now you have your radius being squared. Well, we have another, your radius is 1/2. Your top function is negative x squared minus x plus 2 minus your bottom function, which is x squared minus x minus 2. Okay, so now I'm going to end this parenthesis. Then I'm going to end the green parenthesis. So this is our top minus our bottom, but this 1/2 is included in our radius. So I'll close that parenthesis, and that big old parenthesis has to be squared because that whole thing is your radius. And then dx, of course, to provide the volume aspect because we're stacking them along the x-axis. So again, this looks ugly, but it's just the area of a circle. You're just plugging in the functions. So you've got, it's 1/2 because it's a semicircle, 1/2 pi r squared. You can go ahead and put this whole thing into your y1. Again, be very careful of your parenthesis placement. Put in your correct bounds, and your answer should be 9.478. The hardest thing about these problems is getting your parentheses right because there's a lot of variables and a lot of numbers you have to take into consideration. But when it comes down to it, you're just finding the area of a circle, and that you can do. Now let's do an example with an isosceles right triangle. So again, same two functions. Let's go ahead and let's look at the 3D image so you can see what this looks like and the volume it's creating. Okay, now we're doing isosceles right triangle. So again, I'm going to slide the isosceles right triangle all the way along the x-axis so you can see the shape that this right triangle is creating. And now let's take a look at that volume shape. So here's the volume shape created when we are sliding this isosceles right triangle between those two curves. Now that you've seen the 3D image, let's take an aerial view again. So here is what the bottom of that isosceles right triangle looks like. we're going to take that slice out and I'm going to lay it down so we can see what that looks like. So we have an isosceles right triangle. Here's my right triangle. And now what we have to do is, what's the area of a triangle? Area is 1/2 base times height. And this is the slice that I took out of our function and I laid it down. So how do we find the area of our base? Again, it's top minus bottom. And in this case, our base and our height are the same because it's an isosceles right triangle. So all we have to do over here, when we do the area, 1/2 top minus bottom squared, because our base and our height are the same. So let's set up our function. Again, we're going to have the same bounds because we're dealing with the same two functions. 1/2 our top function, negative x squared minus x plus 2, minus, and I'm going to do another parenthesis because that minus has to distribute through to that whole other function. That function is x squared minus x minus 2. And now this is our base. Oh, got to close my other parenthesis. This is our base. And remember, our height is the same, so we're going to square it. And it's a dx problem because we're stacking these triangles along the x-axis. Now you can put this function into your calculator. If you still have it in your calculator from the last problem, you can easily insert and delete things as needed so you don't have to type out the whole thing again. When you put this into your calculator, you should get 12.068 for your volume. Let's do one more example, the equilateral triangle. This one gets a little bit more tricky. But first, let's go to the 3D image so you can see what it looks like when you're sliding an equilateral triangle between the two functions and the volume it creates. Okay, for this example, let's look at what the equilateral triangle looks like as you slide it along the x-axis between these two curves. So this is the space and the volume that the equilateral triangle is. So this is the volume that is created as we slide this equilateral triangle along the x-axis. So this is the volume that we are solving for. Now that we've looked at the 3D image, again, let's look at the aerial view. Here is the bottom of that triangle that I want to work with. So I'm going to take that slice, slide it out, and I'm going to lay it down. And we're going to have here an equilateral triangle, at least to the best of my drawing ability. This is that bottom piece that I pulled out of that function. So when we do the area of a triangle again, 1/2 base times height, my base is going to be top minus bottom again. That top function minus that bottom function. But now we have to figure out what is the height of this function. And this is where you have to remember your trigonometry. Because I'm going to take this triangle and I'm going to split it in half. So you can see here's my height that I'm taking over here, and here's my triangle. Now we have a 30, 60, 90 triangle. Do you remember your ratios for a 30, 60, 90 triangle? If not, I'm really testing you here. So if you don't remember 30, 60, 90 ratios, 1, square root of 3, and 2. So if I use these ratios and label my triangle, my 30 side is here, here's my 60 side, and here's my 90 side. Well, this is one what? Well, you're going up and down the y-axis. So I'm going to say this is 1y. This is the square root of 3y, and this would be 2y. That's how you get your ratios. So the height of our triangle here is actually square root of 3 y. So let's put this together and see what that means. So we have our integral from negative 1.414 to 1.414, same bounds as before. Area of a triangle, 1/2. My base is my top minus my bottom. So again, negative x squared minus x plus 2 minus my top function, which is x squared minus x minus 2. Close both those parentheses. So this part right here is my base. That's this guy, okay? But I took this whole base and I called that 1y over here. So technically, this y is only half of my base. All right, so what do we have so far? We have 1/2 base. Now we have to multiply by our height. Our height, I'm gonna multiply here, is the square root, I'm gonna write. So our height is the square root of 3y, right? That's what I wrote. But how do we figure out what y is? Well, if we go down here, we know what our y is. Our y is this part right here, which over here corresponds to this piece. So our y is half of our base. So yeah, you gotta put this whole thing in again, which gets to be a little bit much. So follow what I'm gonna do here. I'm gonna leave that y in there for just a second. Now this should be a dx at the end, right? So eventually this guy has to be rewritten in terms of x, all right? But this y is gonna be half of this mess. So this y, I'm gonna do a thought bubble down here, is really 1/2 of top minus bottom, which is this mess all in here. All of these pieces are connected by multiplication. We're gonna simplify a little bit to make this easier to write down. So this piece right here and this piece are the same. I'm gonna multiply this piece, and this piece together. Since they're all connected by multiplication, I can do that. So we'll rewrite the integral, negative 1.414. I'm multiplying together the highlighted green pieces. So 1/2 times 1/2 is 1/4 with the square root of 3 on top. Parenthesis. This piece highlighted in yellow and this piece highlighted in yellow are exactly the same, and we're gonna multiply them so we can just square it. So negative x squared minus x plus 2 minus x squared minus x minus 2. All my parentheses are right. This is in parentheses. And then square it dx. So this would be your equation for the equilateral triangle. So when you put all this in your calculator, you should get 10.451. When you're doing volumes of a solid, the biggest thing you have to know is how do you find the area of the shape that you're looking for, and then put it in dx or dy terms depending on if it's hitting the x or the y axis. You know how to find the area of all these functions. Sometimes it's just complicated because you're using functions and your equations look messy and they're long. But you can do this. So hopefully this video helped you. Be sure to subscribe and share this video with another friend in calculus.